Second day of lecture, and there's two topics we want to cover. The first is Newton's third law, which you might have heard is for every action there's an equal and opposite reaction, but of course in physics we go into a little bit more detail, and in AP Physics we go into a lot of detail. And then the second topic I want to cover, and I hope I cover it in this lecture, otherwise it'll be in the next lecture, we're going to be talking about friction. And for those of you that have had me as a teacher, I know that we talked briefly about friction, but this year we're really going to get into a lot of detail, and we're going to define two different types of friction. One is static friction, and the other is kinetic friction. And they are slightly different as far as what they do, but as far as how you treat them in physics problems, they're remarkably similar. And we're going to be talking about something called a coefficient of friction, which is sort of how we take friction from an idea that we talk about and turn it into something we can work with in the context of free body diagrams, Newton's second law, and equations. So really briefly, static friction is the friction of objects that stand still. You're pushing them, they don't move. And kinetic friction is the friction of objects when you push them and they are moving, but there's a little bit of resistance to the ground or whatever you're pushing them against. So that's what we'll talk about today. So let's get into it. All right, so let's begin. The problem I want to start off with is one that you're going to see quite a few times in the class, and it sometimes appears on the AP, and it's really just a good way to sort of introduce how third law forces work. So you might have seen this problem before in a previous class, and this is sort of a good review of the third law as we use it in AP Physics. So it's a simple problem. We want to determine the contact force and the acceleration of the two blocks below. And in the Google Docs homework, I'll actually give you real numbers, but right now we're going to solve this using letters. So let's be clear on this. The unknowns are the acceleration and the contact force between the two boxes. And one thing I want to be kind of clear on here is when we talk about contact force between boxes, that's a really deceptive term, and I'll explain why in a second. So I'm just going to put a little star here to sort of take note that this idea of a contact force between boxes is actually a little trickier than it seems, and we'll explore that a little bit below. So let's begin first by drawing the free body diagrams for the system. So here I'll draw the free body diagram for M1. And for M1, here's what's going to happen. I'm going to have the force F going to the right. And of course, as always, it's resting on the ground, so I have a normal on 1 due to the surface of the ground, and I have the weight on 1 because Earth pulls down on it, so that's its weight. That's mass times gravity again, so just to remind you, that's M1 times G. And here's the thing. M1 wants to go forward, but it bumps into M2. So that's kind of important, so I'm actually going to write that. So M1 wants to go forward, go to the right, but it bumps into M2. And what this means is that because it bumps into M2, M2 is a barrier. It blocks it. Just like if you walk into somebody, you get pushed back. You walk into a wall and you abruptly you stop. So what we're going to say is there is a force on M1 due to M2, and there are several ways that I'll label this force. One way you'll see it labeled is I'll say that there's a force on 1 because 2 pushes back on it. Other ways that you'll see this written is you'll also see this written as N on 1 due to 2. Either one of these is okay. So you can use either. So either label is fine. Okay? Now, those are all the forces on M1. Now let's label, so this is M1's free body diagram right here. Now what we're going to do is we're going to do the free body diagram for M2. So let's do that right now. Now it's really tempting when you take physics to say, oh yeah, well, the force pushes both the boxes, and that's how we talk in everyday life. But let's be clear. On M2, the thing that's actually pushing it is the fact that it is in contact with M1. So strictly speaking, what's pushing M2 forward is there is a force on 2 because box 1 is actually pushing up against it. And of course we have our other forces, which is the normal on 2 due to the surface, and the weight of 2 due to the Earth. Now, this is what Newton's third law actually says, and I'm actually going to write out Newton's third law right here. So, what Newton's third law actually says is this. It says if box 1, or I'm going to say it for this system. So, if box 1 exerts a force on box 2, that's what this force here is, then box 2 exerts an equal and opposite force on block 1. So let's be clear, that's this force right here. Now, something I want you to notice. First of all, there are a couple properties of third law forces. We're going to examine these in a little bit, but just take note of a couple things quickly. Notice they have the same capital letter, these two forces that are involved in the third law, and their subscripts are switched around. That is a common, those are two things that happen with third law forces. So they happen, or you see them on two different free body diagrams. So these two are third law pairs, and you see them drawn on two different free body diagrams. So one thing I want to take note of right now, okay, this guy right here and right here, those are not third law pairs. So get that out of your head now. The normal force and the weight are in no way third law pairs. Okay? They're not even related. I mean, they have the same value, but that doesn't mean that every force that is equal and opposite to another force is a third law pair. We're talking about contact forces between two specific things, and later on we'll see gravity works that way too. So in other words, 1 pushes 2, 2 pushes back on 1, and the free body diagram labels are in different pictures. Now, once we have that set up, it's actually very easy to solve this problem. So what I'm going to do is this. I'm going to actually write down the equations in black with the variables that we're solving for written in red. So once again, I'm going to read off my free body diagram for 1. So for mass 1, okay, in the y direction, I'm going to have that the normal force, well, technically, we don't really, let's be clear. The normal is an unknown. So then the normal force on 1 due to the surface, okay, is opposed by the weight on 1 due to the Earth. So I'm going to write that as m1g. And those two have a tug of war, and nobody wins that tug of war. Now, for the horizontal direction, we have the applied force, which will be given to you in your Google Docs homework. And we have this contact force. The force on 1 due to 2. These two forces have a tug of war. And the effect is that m1 actually accelerates. Okay? Now, let's set up the equations for m2. It's very similar. You'll see how this works. We set up the equations for m2, and what we're going to get is the normal on 2 due to the surface it's resting on, minus the weight of m2. They cancel out. Those two forces cancel, so the box doesn't fly into the air, nor does it fall into the ground. And then, in the horizontal direction, we're going to have the force on 2 due to 1 makes box 2 accelerate. Now, this is a thing I said I was going to put a little star by and explain later. So this contact force between the boxes, let's be clear on this. The contact force between the boxes, what that really means is this. Find the value of the force on block 2 due to block 1, and that will have the same magnitude, remember what that means, as the force on 2 due to 1. So if you solve for this one, you automatically solve for that one. So what this means is, algebraically, these have the same value. So you can actually, when you solve problems, substitute this into here. And on your Google Docs homework, what I'm going to do is, I'm going to tell you, look, F is going to be 12 newtons, and I'm going to give you M1 equal to 2 kilograms. M1 will be 2 kilograms, and M2, we're going to make that 4 kilograms. And we're going to have you find the acceleration. So what you're going to find for me is, you'll find the acceleration. And when we say the contact force between the blocks, what we mean is find F12, and that'll automatically give you F21. So you can use algebra to substitute into here and here. These will have the same value, but you actually technically have to write them as 2 separate forces because they are 2 different forces in the picture. Okay, so algebraically you can treat them as 1 variable. So we're going to have you solve that. So that's what we'll have you do on the Google Doc. Okay, so you should be decent at setting this up, and that's what you do for homework. Now, I want to go a little bit in depth on third law pairs and how they work and this whole switching of subscripts thing. Let's flip the page. All right, so this is how this is going to work. You've seen a mass sitting on a table. Let's do the free body diagram for this and kind of show you where this is going. So say I've got this mass M here, okay, and we draw the forces, so I'll draw. There's a normal on the mass due to the surface of the table, and there's the weight of the mass due to the Earth. And in the last page, I told you guys that these are not a third law pair. What we actually have to do is follow this procedure here to figure out what the third law pair is. So this is what I mean. I say take a force with 2 subscripts. Okay, there's one right there. Switch the subscripts. So to switch the subscripts, I'm going to take this N, S on the surface due to the mass. And I'm going to reverse the arrow direction. Now, I have to place it on the correct free body diagram. Technically speaking, let's look at this. We've got the normal that is applied to the surface of the table from the mass pointing down. So what that means is there is a force on this table pointing down due to mass 1. So this is 1 third law pair right there. And this is the force that basically puts scratches on the table and messes it up, and so why you put placemats and heating pads and all that other stuff. Okay, so that's what that third law pair is. Now we still have this one here. We have the weight of the mass due to the Earth, so there's 1 third law pair. One member of a third law pair. Now what do? Again, we have to reverse the subscript, so I have W on E due to M. Well, let's remember what weight is. Weight is the gravitational force on M due to Earth. So WME must be the gravitational force on Earth due to M. So gravitational force on M due to Earth, and this is the gravitational force on Earth due to M. In other words, what I'm literally saying is that this mass, okay, we'll pretend we're in California, okay, we have a table in California, is literally applying an invisible gravitational force to the Earth that pulls up on it invisibly. The thing is, the Earth has over 10 moles of kilograms mass, so the acceleration that's going to cause is so negligible. You can't measure it. It's that small. There's no point in even trying. So there is a force applied to the Earth by virtue of the fact that there's gravity. There's a gravity field put out by this mass that actually pulls up on the Earth. And that's what we're drawing here using Newton's third law. So this is a subtle point. And I would actually strongly recommend watching this part of the video again to kind of make it clear what these third law pairs are and how they work. And in fact, I'll zoom out just a little bit so you can see this whole picture here. So take a look at those and really understand how this works. If you have questions, ask me in class. And that's it for the third law. We'll take up friction in our next lecture.